Okay, we're going to take a little math break here for just 1 second, because I need to establish that you know some things about, well, exponents, and we're going to get into logarithms here. So just to refresh your memory, and we've been doing this with scientific notation a little bit, 10 to the power of 1, well, that's basically the same thing as 10, right? 10 to the power of 5, basically the 5 gives us the number of zeros in that number. So we're going to have, in this case, we're going to have 1, 2, 3, 4, 5. So it's 100,000 is 10 to the 5. 10 to the negative 3. This is going to be a decimal number now. So 0.001. Okay. The negative 3 basically dictates how many places the decimal moves over. So it's going to be 1, 2, 3. That was 1, 2, 3 places it moves over. So 10 to the negative 3 is 0.001. 10 to the 0.5 is basically it's something you might want to use your calculator for, but it's not a negative number. This 0.25, it's not a positive, it's not an integer. Basically, this is the cubed, not the cubed, but the fourth root of 10. So on a calculator, it would be 10 x to the y, 0.25. In this case, works out to, so 1.778. Okay. So let's try these ones here. 10 to the power of x gives us this number here. Basically, just need to count the zeros. 1, 2, 3, 4, 5, 6. Okay, so in this case, x is equal to 6. 10 to the power of 6 will give us this number. 10 to the power of x gives us this number. Okay, in this case, x is 1, 2, 3, 4, 5, negative 5. Okay, because the decimal went over 5 times. Okay, so now let's consider 10 to the x is equal to 5.876. That's a little tougher. 10 to the x is equal to 3.2. I think we're going to need a special kind of function in order to solve those. Let's skip ahead here and see what this log thing is about here. Log of 1 million. Well, basically what that means, the answer to that one is 6. What that really means is since 10 to the 6 is equal to 1 million, we can also say if we take the log of 1 million, what we're saying is 10 to the power of what will give us that 1 million. So since 10 to the power of 6 is 1 million, log of 1 million is 6. So in this case, log of 0.0001, what we're saying is 10 to the power of what will give us 0.0001. Well, 10 to the power of negative 1, 2, 3, 4 gives us 0.0001. So log of 0.0001 is negative 4. Okay, but we don't have to be able to figure it out by hand like so. We can actually just use our calculator to figure this out. So log of 5.5, 10 to the power of what gives us 5.5? Well, let's just use our calculator to figure that out. Okay, clear this off. 5.5, and then find the log button, press log, 0.74. So the answer here is 0.74. 10 to the power of 0.74 will give us 5.5. Can we check that? Yeah, maybe we can. Let's see. Clear. 10, and then let's see, a y to the x button. Yeah, x to the y, and now 0.74 equals 5. Okay, so something very close to 5.5. Okay, so when we're doing 10 to the x is equal to 5.876, the way to solve this is really to do a log of 5.876. Okay, and log of 5.876, if we use our calculator here, take the log, 0.769. 10 to the x is equal to 3.2. That's a tough one. We can't just do it in our head, so let's use a log. Take the log of 3.2, and that equals the log button 0.505. Okay, so there we go. Some different questions. Log of x is equal to 8. Okay, so log of x is equal to 8. In other words, 10 to the power of 8 is going to give us x. So x is equal to 10 to the power of 8. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 6, 7, 8. Yeah. Okay. That was a bit messy. Log of x is equal to -3. In other words, x is equal to 10 to the power of -3, or 0.001. Okay, so that's how you would solve those. I know I went through that quickly. Hopefully you've had some exposure to that in math class as well. In neutral water, concentration of hydronium, remember this is the hydronium ion right there, is made up like so. So water, as you can see, is in an equilibrium type of condition. So water and water get together and they'll form a hydronium and a hydroxide when they kind of bang into each other and they ionize. And this is sort of a temporary thing. They'll go back and forth between being ions and being water. So they go back and forth, water ions, and but basically, as you can see, you've got an equal concentration of your hydronium as you do with your hydroxide. So there should be an equal amount of each. These square brackets are a way of representing concentration. So we could state this as the concentration of hydronium is equal to the concentration of hydroxide. This would be in neutral water. Okay, so there we go. Now the actual concentration of hydroxide ions in neutral water and the actual concentration of hydronium ions in neutral water is 10 to the power of -7. Okay. When the concentration of hydronium rises, we end up getting so water plus water gives us so a large concentration of hydronium and kind of a lower concentration of hydroxide. And so when you rise that concentration of hydronium, it will react with some of these hydroxides and kind of switch, move more of the products into the reactants, but generally you'll have an abundance of the hydronium and you'll end up with an acidic solution. When the concentration of hydroxide rises, then of course you're going to end up with a basic solution. Some of those hydroxide ions are going to react with the hydronium and you'll end up with more of the water coming out, but still you'll have an overall basic solution because of an abundance of hydroxide ions. Okay? So as we think through this and as we're analyzing how much hydronium we have, how much hydroxide we have, what the concentrations are, an easy way of dealing with this, because we're dealing with such small concentrations when it comes to hydroxide and when it comes to hydronium, we need a way of tracking these concentrations without dealing with these unruly numbers. So way back a long time ago, scientists started to refer to the concentration of hydronium ions by taking what's called what's the negative log of hydronium and we refer to that now as pH. And that's how the pH scale is defined. And you've known from grade 10 that the pH scale goes generally from 0 up to 14. And neutral water has a pH of 7, right? Well, now you can see why. It's because neutral water has a hydronium concentration of 10 to the negative 7. So if we take the negative log of hydronium for neutral water, the pH is going to be equal to the negative log of 10 to the negative 7. Okay, which is equal to negative, okay, log of 10 to the negative 7. 10 to what power will give us 10 to the negative 7? Negative 7. Okay, so the negative of negative 7 is just 7. So it makes sense that 7 would represent neutral water. That's where the hydronium concentration is exactly 10 to the negative 7, and that's in moles per liter. So the pH of distilled water is 7. The pH of a solution with a hydronium concentration equal to 5 times 10 to the negative 3 moles per liter. Okay, well, pH is equal to negative log, okay, 5 times 10 to the negative 3 moles per liter of hydronium, okay, is equal to 5 times 10 to the negative 3. Take the log of that, okay, and then we take the negative log of that, 2.301. Okay, if we wanted to find the pH of a solution which has 3 moles per liter hydrochloric acid, we would have to remember that HCl gets together with water is going to make hydronium plus chlorine ion. Yep, so it's a 1-to-1 molar ratio. So for every mole of hydrochloric acid that we put into water, we're going to end up with a mole of hydronium ion. So we can basically just take 3 moles per liter as the concentration of hydronium in this case. So the pH is going to be equal to the negative log of 3. Okay, so we take the calculator out. 3 log 0.477 and then negative. So negative 0.477. Okay, almost 0. So very, very acidic when we have 3 moles per liter hydrochloric acid. Okay, this question here, a solution with a pH of 9 has a hydronium concentration of, okay, so a pH of 9. What we have to do here is we have to say, okay, so pH is equal to 9, okay, and that's basically equal to negative log of the concentration of hydronium, and we'll have to work backwards from there. So what does that mean? Log of this number is 9. So in other words, 10 to the power of 9 is equal to the hydronium concentration. So we can rewrite this as hydronium concentration is equal to 10 to the power of negative 9. Okay, so in other words, 0.1, 2, 3, 4, 5, 8, oops, 8, 9. 1, 2, 3, 4, 5, 8, 9. Yeah. Okay. That does it for pH for now, and we'll see you on Monday for some more exciting practice problems.